Welcome to this explainer. Today, we're diving straight into something absolutely fascinating: graph neural networks, or GNNs. It's this wild technology that is literally reshaping how artificial intelligence understands all the complex, messy data out there in the real world. We're going to unpack the foundations, the cutting-edge stuff, and the incredible applications of what's become one of the fastest-growing topics in machine learning. Seriously, if you want to understand the future of AI and how we make sense of our highly connected world, you've got to understand graphs. Let's get into it.
Think about it. When we look up at the cosmos, we don't just see isolated, lonely stars, right? We see constellations, solar systems, galaxies, these incredibly complex gravitational relationships tying the whole shebang together. Well, modern data operates exactly the same way. Information is rarely just sitting there in isolation. It's deeply interconnected. And here's the kicker. The relationships between data points are often just as critical as the data points themselves.
So here is our roadmap for today's explainer. First, we'll look at the next AI frontier. Then, the language of graphs. Third, we'll break down how GNNs actually work. Fourth, pushing the boundaries. And finally, real-world applications. All right, Section 1, the next AI frontier and why we actually need this stuff. You know, traditional machine learning relied really heavily on this thing called feature engineering. Basically, that meant humans had to painstakingly extract and define features based on their own knowledge before even feeding it to a computer. It was incredibly labor-intensive, relied way too much on domain experts, and honestly, worst of all, those extracted features could be highly biased just because human knowledge is inherently limited. But deep representation learning? Oh, it changes the game. It's automated, it finds those hidden patterns entirely on its own, giving us much better abstractions without a human slowing down the whole process. And this brings up a fantastic point made by Bo Zhang, a highly respected member of the Chinese Academy of Science. He noted that GNNs have this immense potential to combine probabilistic learning, making educated guesses based on data, with symbolic reasoning, which is actually understanding the underlying logic and rules. So this isn't just some minor incremental update, it is a massive shift in how computers understand our world, actively nurturing what experts are calling third-generation AI.
Moving right along to Section 2, the language of graphs, and this brand new AI landscape.
Okay, so just like those stars we talked about form recognizable constellations in the night sky, a graph in computer science is basically made of two main things. First, you have a node set, which represents the actual entities or data points, and second, an edge set, representing the specific relationships between them. These nodes and edges combine to form the underlying topology or structure of the graph. But it's not just bare structure. These nodes, edges, and even the whole graph itself can hold incredibly rich information, acting as features or attributes to really give the AI some much-needed context.
Now, things get even more interesting when we introduce heterogeneous graphs. This is a scenario where the nodes and edges come in a bunch of different types. Think about a knowledge graph for a second. You don't just have one type of entity or one single type of relationship. You have thousands. You might have people, places, and organizations all connected by entirely different actions. Heterogeneous graphs are amazing because they allow us to capture the true, messy, multi-layered complexity of the real world. Because let's face it, real-world data is almost never a neat, uniform spreadsheet.
Depending on the specific problem we're trying to solve, we can actually ask our machine learning models to focus on different levels of the graph. We usually categorize these into three main tasks. First up are node-level tasks, like node classification, where we just want to determine the category of a single specific entity. Second, we have edge-level tasks, like link prediction. That's where the goal is to predict if a brand new connection should exist between two nodes. And third are graph-level tasks, like graph property prediction, where we zoom all the way out and analyze the overall characteristics of the entire graph as one single entity.
All right, let's get into Section 3, how GNNs actually work, unpacking the mechanics.
Okay, the absolute secret sauce here is this brilliant framework known as message passing. In a message passing setup, the key step in each and every neural network layer is to literally pass messages between different nodes, all based on the structure of the graph. Crucially, though, in most standard setups, information only flows between nodes that are directly connected to each other. This localized updating kind of acts like a filter, allowing the network to essentially learn the very shape of the graph right around each individual node. It's really clever.
By following three exact steps, the algorithm translates a massive, tangled web into something actually usable. Step 1, network embedding. This is where it represents each node as a low-dimensional mathematical vector.
Step 2 is the message passing phase, which applies graph convolutions, basically blending features between neighbors so they can share information. And finally, step 3, the readout phase, which is sometimes called pooling. This summarizes that localized node information to form high-level representations. This elegant little process turns a totally chaotic web of relationships into clean math that a computer can easily process.
Now, just to give you a sense of the sheer scale and data hunger these deep learning models require, let's step outside of graphs for just a second. In computer vision, datasets like ImageNet contain 1.3 million manually labeled examples, covering 1,000 different classes. And get this, that is just to train the basic visual feature kernels from scratch. Well, graph neural networks are equally data hungry. They leverage massive topologies to learn profound representations, which, yes, requires immense computational power, but it yields unprecedented accuracy in return.
Moving on to Section 4, pushing the boundaries and exploring those theoretical limits. The frontier of graph machine learning is expanding just as rapidly as the data universe itself. As the field makes these rapid, honestly incredible strides, researchers are discovering that scaling these models to massive, real-world datasets introduces entirely new sets of challenges. Challenges that need absolutely brilliant solutions. Researchers all over the globe are actively tackling these massive challenges right this second. Take adversarial robustness, for instance. They're figuring out how to defend models against malicious perturbations that are specifically designed to trick the AI. Or scalability. They are inventing new ways to smartly sample nodes and layers so we can process massive networks without totally crashing our computers. They're also tackling dynamic graphs, which involves handling nodes and edges that constantly change over time. And of course, interpretability, which is the absolutely crucial task of explaining exactly how these highly complex black box models are actually making their decisions.
And finally, Section 5, real-world applications, and how this is transforming industries.
Let's pause for a second because I really want to emphasize that these aren't just academic exercises. They are fundamentally transforming real industries and solving critical human problems. In e-commerce, GNNs power modern recommender systems by analyzing massive webs connecting users to items, suggesting exactly what you might want to buy. In drug development, biomedical knowledge graphs are used for hypothesis generation. This even included vital COVID-19 drug repurposing. Urban intelligence relies on them for traffic configuration and finding anomalies in smart cities. And in biology, they're making massive strides in predicting the exact way proteins function and interact with each other. It's truly amazing.
The bottom line here is that graph neural networks are already taking the scientific and industrial world by storm. From uncovering malicious software and detecting spam accounts, all the way to advancing cross-media computer vision and natural language processing, GNNs are definitely no longer just a niche research topic. They are a foundational tool that is literally reshaping our entire technological landscape.
So as we continue to unlock all these hidden connections in the data all around us, combining symbolic reasoning with incredible data-driven deep learning, I want to leave you with this final thought. As these systems get smarter and more integrated, how will these invisible networks, these graph neural networks, remap the future of your world?